Imagine a bird you'll never meet again. It's midnight on the coast of Alaska. The sky is black, the ocean is darker, and a tiny shorebird, lighter than your phone, launches itself into the wind. No test flight, no practice run. It just lifts off and heads south, straight out over 7,000 miles of empty Pacific. No islands, no gas stations, no second chances. For more than a week it flies, non-stop, through storms, through clouds, through total darkness. Its heart is pounding, its fat reserves are burning, and if it misses, that's it. But this bird doesn't just hit the right country. It drops out of the sky onto the same scrap of New Zealand mudflat its species has used for generations, within a few hundred meters. What if I told you it's never seen that place before? Now swap the roles. I blindfold you, spin you around a few times, throw you on a plane, and drop you 3,000 miles away in the dark. No phone, no map, no signs. You'd think you could at least guess the right direction, right? Nope. Most of us can't even leave a shopping mall without checking which parking lot we're in. This bird? It's basically born with the mall map printed in its brain. A walnut-sized brain, by the way. Not a supercomputer, not a military satellite, just a squishy little bundle of neurons that somehow outperforms your GPS, which, let's be honest, sometimes freaks out in a tunnel and has to recalculating route, like it's doing rocket science. Believe it or not, scientists have tried to break this system. They've moved birds thousands of miles off course, raised them under fake stars, even messed with magnetic fields around their cages. And the birds still try to fly home. They act like they can feel the planet turning under them, like the whole Earth is a giant glowing sign that only they can see. So what's going on inside that tiny head? These animals aren't using just one compass. They're running a hidden cocktail of senses all at once. A magnetic field detector in the eyes, an internal star chart, a smell-based map of the ocean, mental pictures of coastlines and mountains, and inherited flight plans passed down like family recipes. How's that for a navigation app? But here's the twist. In a single human lifetime, we've started rewriting the sky this system evolved in. We've flooded the night with city glow, radio noise, glass towers, and spinning wind turbines that can turn a clean migratory highway into a deadly obstacle course. Routes that took millions of years to perfect are getting scrambled in a few decades. So in this video, we're going to pull this superpower apart, one sense at a time. We'll look at the experiments that proved birds really can see magnetic fields, read the stars, and smell their way across oceans, and then we'll see how modern life is quietly breaking each one. And guys, one of the absolute best things you can do is stick around, because at the end, I'll show you what you can actually do to help keep this invisible map from vanishing. So now that we know birds are running this invisible operating system, let's talk about just how insane the road trip actually is. Because on paper, these migrations should not work. At all. Imagine a creature the size of your phone doing the ultimate around-the-world flex. Arctic terns leave the Arctic, swing all the way down to Antarctica, then come back again, tracing looping routes that can add up to 70,000 kilometers a year. That's almost twice around the planet, on wings that weigh less than your car keys. You'd think that was the record, right? Nope. Bar-tailed Godwits look at that and go, cute. These birds launch from Alaska and fly more than 11,000 kilometers to New Zealand in a single, non-stop shot over the Pacific. No refueling, no island hopping, no floating rest stop shaped like a convenient cruise ship. Just days of continuous flight over empty shifting water. And then there are the rebels, young cuckoos. Their parents literally ditch them in another species' nest, Never show them the route. Never give them a practice run. Yet on their very first migration, these teenagers with feathers cross continents to Africa, alone, and land in the same general wintering grounds as adults they have never met. Believe it or not, that's all on a program written into their DNA. Now, think about how hard this should be. There are no road signs over the ocean, no highway exits. Half the time, there isn't even a visible coastline, just horizon in every direction. Winds change, storms shove them sideways, and the earth itself is curved, constantly trying to nudge them off what looks like a straight line on our flat maps. Meanwhile, you miss one turn when your phone GPS drops for 10 minutes in a tunnel, and suddenly you're 30 minutes late and yelling at an inanimate dashboard. These birds? They fly for days or weeks with no visible signal and still nail specific estuaries, the same patch of forest, sometimes even the exact backyard tree they used last year. How's that for making your navigation app look a little basic? So what's going on under the hood? Scientists are starting to realize birds don't just have one trick. They're stacking navigation layers, an internal compass that tells them which way is north or south, an internal clock that keeps track of time of day and season, a rough mental map of the world, and on top of that, a set of rules wired into their genes, then refined by experience and by following older birds, like a living, flying tutorial. And here's where it gets really weird. When researchers tried to cheat, the system didn't break. They kidnapped birds and moved them thousands of kilometers off course. They messed with the sky in planetariums. They scrambled the magnetic field. Yet the birds still often corrected and headed home, as if they were sensing something we can't feel at all. What if I told you that hidden sense might literally let them see the planet itself, and that in the next part, we're going to try to pry it open? But here's the twist. Before we talk about that secret sense that might let birds see the planet, we have to talk about something even stranger. Imagine being born with travel instructions already loaded in your brain. No maps, no GPS, no parents giving you directions, and you still know roughly where to go. That's what a lot of migratory birds get on day one. They come pre-installed with a kind of flight program. It doesn't give them a street address. It's more like, fly this direction, at this altitude, for this long, during this season, then stop. You'd think that sounds way too simple for a 10,000-kilometer journey, but it actually gets many of them shockingly close to the right continent, and even the right region. The most insane example? Cuckoos. Young cuckoos never meet their real parents. The adults lay an egg in another species' nest, vanish, and leave the foster parents to raise this totally different-looking chick. No one sits this bird down and goes, "So, Africa is that way." Yet when migration season hits, that young cuckoo launches into the sky completely alone and heads for Africa along the same ancient flyways its ancestors used. No flock to follow, no practice runs, just a built-in route. Believe it or not, these birds cross thousands of kilometers of land and ocean on a trip they have never done before, to a wintering ground they have never seen. How's that for? Some animals are just built different. Scientists didn't just take this on faith. They tried to break it. In classic lab experiments, they put migratory birds in special cages during migration season. The birds can't actually fly anywhere, but their bodies still know it's time to go, so they start scratching and hopping in the direction they're trying to migrate. It's called migratory restlessness, or Zugunruha if you want the fancy word. Here's where it gets fun. Rotate the cage, and the direction of the scratching rotates with it. Fake a different night sky in a planetarium, and the birds shift their "let me out" scratching to match the new star pattern. change the cues, change the direction, like they're reading a set of internal rules and checking them against whatever sky they see. So when we say genetic instructions, we're not talking about a literal map rolled up in their DNA. It's more like a list of rules. Fly southwest for this many weeks, then adjust more south. Leave when the days get this short. Climb when the air feels like this. It's a recipe, not a Google pin, but it's good enough to get a young bird to roughly the right coastline, the right river valley, the right side of a mountain range. But here's the catch. Roughly right isn't what we actually see in the wild. We see birds hitting the same tiny island, the same forest patch, sometimes the same tree, year after year. Genetic autopilot alone shouldn't be that precise. So something has to fine-tune the final approach, and that something gets even weirder once we look up at the sky in the next part. So if genes only get birds roughly right, who's teaching them to nail the exact river bend, the exact bay, the exact lonely tree in the middle of nowhere? The answer starts in a weird little window right after they hatch, when their brains are basically wet cement. Imprint that, and you imprint their world. You'd think imprinting is just, this is mom, don't lose her, but it's bigger than that. In those first days and weeks, young birds lock on to parents, the skyline, the smell of the marsh, the way the sun falls on a particular valley. They're not just learning who they are, they're downloading a mental screenshot of home that will anchor every epic flight they take later. Now imagine you're a young goose on your first migration. You don't read maps, you read mom's tail feathers. Flocks of geese and cranes turn migration into a moving classroom. Juveniles literally shadow the older birds, wingbeat for wingbeat, as the family threads through mountain passes, skirts along coastlines, and drops into the same rare, safe wetlands year after year. It's a multi-generational road trip where the directions are sung and flown, not written. Watch a line of sandhill cranes snaking down a river valley. The adults at the front know every bend, every power line, every field where the farmer doesn't mind a few extra beaks. The young ones are memorizing all of it, turning landmarks into a living GPS. Miss that first trip, and you don't just miss a vacation, you miss the whole route. Believe it or not, humans have crashed this family driving lesson and taken the wheel. There are projects where conservationists hand-raise endangered cranes, then hop into tiny microlight aircraft and lead them south like some bizarre ultralight goose. Yeah, you heard me right. A rare, nervous, leggy bird chasing what is basically a flying lawn chair. And it works. Those cranes imprint on the aircraft as parent, follow it along a brand new path, and then, in later years, repeat that same route on their own. What if I told you we literally reprogrammed their migration, not by editing DNA, but by editing who they followed on that first big trip? That's the power of what scientists call cultural flyways. These are invisible sky roads that live in memory, not in genes, passed down like stories around a campfire. Lose the elders in a flock of geese or cranes, and you don't just lose experience. You can erase entire maps from a population in a single bad winter or one more drained wetland. So now we've got genetic autopilot, family instructors, and traditions etched into the sky. But there's still one brutal problem. What happens when the clouds roll in, the land disappears, and the sea looks exactly the same in every direction? To keep going, birds need something even stranger than family stories. They need a way to know which way is north when north is completely invisible. So when north is invisible, birds do something wild. They fly by a moving star. Imagine you're a tiny songbird over the open ocean. No mountains, no coastline, just water and sky. You'd think that's a guaranteed way to get hopelessly lost, right? But this little creature looks up, checks the sun like it's a glowing compass needle, and somehow knows exactly which way to go. Here's the basic trick. The sun rises in the east, sets in the west, and crawls across the sky in a pretty predictable arc. Birds have learned to treat its position as a giant compass, but with a catch. You can't use the sun unless you also know what time it is. So inside that walnut-sized brain is an internal clock, a circadian rhythm, quietly ticking away and telling the bird, "Hey, it's about 10 a.m. The sun should be over there." Direction plus time equals heading. What if I told you scientists have actually watched this in action? In the classic experiments, they put migrating birds in circular cages, kind of like tiny arenas, and shined an artificial sun from one side of the room. The birds started hopping and fluttering toward the direction they'd normally migrate. Then the researchers did something sneaky. They moved the fake sun. Instantly, the birds rotated their preferred direction to match the new east or west, as if the whole world had just spun around. And it gets even better. When scientists messed with the birds' internal clocks by shifting their day-night cycle, the compass broke in a really specific way. The sun stayed in the same spot, but the birds' brains thought it was a different time. So their takeoff direction rotated by exactly the amount their inner clock had been shifted. That's not random guessing. That's a built-in watch talking to a built-in compass. This internal clock isn't some rare superpower either. It's the same kind of circadian rhythm you use when you feel jet-lagged, just tuned for survival instead of complaining about red-eye flights. Birds learn that at dawn the sun is low in one part of the sky. At noon, it's overhead. In the evening, it slides down the other side, and they constantly adjust their angle to stay on course. But what happens when the sun disappears behind clouds? Game over? Believe it or not even close. Birds can detect polarized light, those invisible patterns in the sky that our eyes just completely ignore. Even when the sun is hidden, or has already dipped below the horizon, those patterns still point back to where the sun actually is. It's like having a backup compass baked into the blue of the sky. And now comes the twist. Many of the most extreme migrants, especially small songbirds, don't even travel by day. They fly at night, on purpose, when the sun compass is useless. So what do you use when your main star clocks out? Yeah, you heard me right. Some birds literally learn the rotation of the stars and build a night sky map in their heads. So now, picture this. The sun drops, the sky goes black, and that tiny warbler that weighed less than a handful of paperclips suddenly launches into the dark like it's clocking in for the night shift. No GPS, no streetlights, just open sky. You'd think that is the worst time to travel. For a lot of birds, it's the only time. Warblers, thrushes, buntings, all these small songbirds are what we call night migrants. They take off after sunset, climb a couple thousand feet up, and then just keep going, all night. They dodge overheating, avoid daytime predators, and ride smoother winds. Smart move. But it raises a nasty little question. When the sun compass is gone and everything above you is just dots on black velvet, what on earth do you steer by? Believe it or not, one of the best answers came from locking birds in a fake night sky. In the 1960s, researchers took young indigo buntings, these bright blue little creatures, and raised them under a planetarium dome. No real sky, no real horizon, just projected stars. Then they spun the sky in different ways to see what the birds would do. Kind of a cosmic prank, but with science. Here's the twist. The buntings didn't care about the brightest star or some special constellation we humans obsess over. What they locked onto was the rotation. Night after night, they watched the stars wheel around a single still point near Polaris, the North Star. When the researchers shifted that rotation center to a totally different spot, the birds reoriented their migration direction to match the new fake north. Change the pivot, change the heading. So during their first weeks of life, while they're still hanging out near the nest, these young birds are basically pulling an all-nighter astronomy course. Imagine a baby animal just sitting there, staring up, as the whole sky spins. They imprint on the invisible axle of that spin, turning the entire dome of stars into a giant compass rose. Once that pattern is burned in, they can launch on their first migration and keep a constant angle to that pivot, even though they've never flown the route before. And the elegance of it is wild. The bird doesn't need to know what a galaxy is or how far away anything is. It just needs the pattern. Keep this cluster of stars a little to the left, that pivot point over your shoulder, and you hold your course for thousands of miles. How's that for a brain the size of a walnut, outsmarting your car's navigation system the moment you lose signal in a tunnel? But here's where it gets really weird. On cloudy nights, the stars vanish. In storms, even the sun is gone. Yet some birds still migrate straight, even when scientists put them in sealed, windowless containers where they can't see any sky at all. So if they can fly without sun and stars, what invisible compass are they reading next? What if I told you the answer is something you and I can't see at all? Imagine flying through total darkness, no sun, no stars, no landmarks, and still knowing exactly which way is home because you can feel the planet itself. Yeah, you heard me right. A lot of birds seem to have a built-in magnetic sense, like a secret sixth sense tuned to Earth's invisible force field. We walk around blind to it. They treat it like a glowing highway in the sky. The first clues were honestly kind of spooky. Homing pigeons released from towns they'd never visited still arrowed back to their lofts, crossing mountains and cities as if they had Google Maps in their skulls. You'd think once you take an animal far outside its usual stomping grounds, it would at least get a little lost, right? Nope. Many of them came back on a straight line. Scientists pushed it further. They put migratory birds in sealed, windowless containers during migration season. No sun, no stars, no wind cues, no visual landmarks at all. And those birds still tried to hop or flutter in the right compass direction, pressing against the side of the box that pointed toward their normal route. It's like locking you in a closet in New York, and you somehow insisting, very confidently, that home is that way. Then came the weirdest twist. Researchers snuck tiny magnets onto birds' heads or created small artificial magnetic fields around them. Change the field, and the birds change direction. Scramble it, and their orientation got scrambled too. Believe it or not, you can literally jam some bird's internal compass with a magnet the size of a coin. So what exactly are they reading? Picture Earth as a giant bar magnet stuck through the planet, with invisible lines of magnetic force looping from one end to the other. Near the equator, those lines are more horizontal. As you move toward the poles, they tilt and dive into the ground, and the field gets stronger. Angle and strength shift with latitude, like a built-in grid painted on the air. If you're a bird, that's insanely useful. On a cloudy night when the stars vanish, the magnetic field still points you toward north. The angle of those lines can give you a rough idea of latitude, like, okay, I'm at the middle of the planet versus closer to the pole. Over empty ocean with no coastline, it lets you notice drift and subtly correct your path, which is how bar-tailed Godwits can cross 7,000 miles of Pacific with no floating road signs. But here's the catch. For decades, we knew birds were reacting to magnetism, yet nobody could find the actual compass in the body. Was it iron particles in the beak? Special cells in the ear? Some quantum trick in the eye? That mystery led to some of the strangest bird experiments you can imagine, and the real answer turns out to be even weirder than a simple magnet hidden in their skull. And once you see where that compass probably lives, you'll never look at a bird's eye the same way again. So once scientists realized birds weren't just winging it with vibes, the hunt was on for the actual hardware. If there was a built-in compass, where was it hiding? You'd think something that powerful would be obvious, like a bright red GPS button on the beak. Nope. Imagine a lab table covered in tiny pigeon heads. That was real life for a lot of researchers in the 1970s and 80s. They dissected beaks, inner ears, even scraped out tissue grain by grain, searching for microscopic crystals of magnetite, an iron oxide that acts like a permanent magnet. The idea was simple but wild. Maybe birds had millions of nano-sized compass needles buried in their faces. The original hypothesis sounded almost too clean. Clusters of magnetite in the upper beak, wired straight into nerves, tugging ever so slightly when Earth's magnetic field pulled on them. Those tugs would change the firing of those nerves, and the brain would read that pattern as north, south, or you're way off, turn now. A tiny mechanical compass hardwired into a living animal. How's that for a navigation upgrade? And on the surface, it looked like the story checked out. Some groups claimed they'd found neat rows of magnetite cells in homing pigeon beaks, perfectly placed along branches of the trigeminal nerve, which connects face to brain. Others reported iron particles in the inner ear, like extra-sensitive balance organs tuned to the planet itself. You'd think, case closed, right? Not quite. Scientists started doing the obvious stress test. Slap magnets on the birds and see what happens. In orientation cages and release experiments, they put strong magnets near the head, or glued them to the beak like some cursed bird jewelry. And in some cases, the birds really did get confused, circling the wrong way, taking longer to pick a direction, or heading off at weird angles instead of straight home. Believe it or not, that chaos was exactly what people wanted to see, because it seemed to prove there was a physical compass you could scramble. But science has a mean plot twist. Later teams went back to those famous magnetite cells with better microscopes and better stains. And what if I told you many of them turned out not to be fancy compass organs at all, but regular immune cells stuffed with iron, or even artifacts from the way the tissue was prepared? Yeah, you heard me right. The supposed compass might have been the bird equivalent of rusty dust. Suddenly, the iron in the beak story didn't look so bulletproof. Some experiments still hinted that iron particles might play some role, maybe as backup sensors or in a few rare species. But the clean, mechanical compass model started to crumble, and the field was left with a really uncomfortable question. If not this, then what? Because while everyone was staring at beaks and ears, the real breakthrough was quietly forming in a completely different place. Not in chunks of metal, but in delicate molecules. Not in the nose, but in the eyes. And it doesn't just bend biology, it drags us straight into the quantum world. Imagine this: a bird looking at the sky, and hidden in that normal, everyday view is a built-in compass, quietly glowing in the background. Not in some sci-fi cybernetic implant, but in actual living cells in the eye. You'd think that sounds like a Marvel origin story, but it's just Tuesday in the life of a European robin. The key players are these rare little proteins called cryptochromes. They sit in the retina, they love blue light, and in most animals, they're part of the clock that tells you when it's day, night, or time to regret that third coffee. For years, scientists thought of them as simple timekeepers. But then evidence started piling up that in birds, these same molecules were moonlighting as magnetic sensors. One protein, two jobs. How's that for multitasking? The big clue came from some beautifully evil experiments with European robins in captivity. Researchers let the birds orient for migration under different kinds of artificial light. Under normal, dim blue-green light, the robins lined up in the right migratory direction like little feathery compasses. But switch the lights to certain bright or pure yellow wavelengths, and boom! Their magnetic sense just fell apart. They flapped. They fussed. They pointed every which way except where they were supposed to go. Change the light back to that dim blue-green, and the compass came back online. Same bird, same cage, same earth, different light. Believe it or not, that screams one thing. Whatever magnetic trick they're using depends on light hitting those cryptochromes in the eye. No light, no quantum magic. Here's where it gets wild. When cryptochrome absorbs a photon, a tiny packet of light, it kicks off what's called a radical pair reaction. Don't panic at the term. Just imagine two electrons that used to be together get yanked apart into a pair of molecules, but they stay linked by their spins, like tiny bar magnets that can be either aligned or opposed. Earth's magnetic field is incredibly weak, but at this microscopic scale, it's just strong enough to nudge how those spins line up. That tiny nudge changes which chemical products cryptochrome makes, and crucially, the amount of change depends on the direction the bird's head is pointing relative to the magnetic field. Rotate the bird, you rotate the chemistry. What if I told you that means the magnetic field is literally being written into the bird's vision as a pattern of more or less reaction happening across the retina? So when a robin looks out at the world, it might see a faint, ghostly shading or grid laid over the normal scene. Trees, horizon, stars, and on top of that, a dim band or halo that tilts and slides as the bird turns. It's not north in words. It's a feeling of direction painted straight onto the image. Yeah, you heard me right. This animal might actually see magnetism. But this quantum compass has a problem. It's fragile. The same way a radio station gets drowned out by static. These delicate spin states can be scrambled by electromagnetic noise from things like power lines, broadband, and other human tech. In some cities, robins literally lose their magnetic bearings when the EM smog gets too strong, then recover when the noise is blocked. We're only just starting to test how bad this is, and in the next part, we'll look at what happens when our glowing, buzzing world collides with a navigation system built on quantum whispers. So here's where it gets really weird. We didn't just build a noisy, glowing world around these birds. We accidentally built something that can reach straight into their quantum compass and flick it off like a light switch. In the lab, European robins became the canary in the coal mine for this. Imagine a little songbird that normally orients beautifully to Earth's magnetic field in a simple test arena. You put it under a fake night sky, change the magnetic field, and it turns in the new north direction. No problem. Except, in cities, scientists noticed something embarrassing. The birds just spun around. No clear direction. Total confusion. You'd think it was some huge radio tower blasting them, right? Believe it or not, when researchers in Germany started digging, the culprit wasn't one big transmitter at all. It was the background hum of everyday life. Low-level radio frequency noise in the 20 kilohertz to megahertz range, the kind you get from power lines, dimmer switches, cheap electronics, Wi-Fi routers, and 1,000 other gadgets humming away in the walls. Here's the twist. When they put those same confused robins inside a grounded Faraday cage, Basically, a metal room that blocks external electromagnetic fields. Something magical happened. The birds snapped back into alignment. Same animals, same test, same city. The only difference was that the EM smog was filtered out. How's that for a plot twist? You clean up the invisible background, and suddenly the compass works again. This is where the quantum part bites us. That magnetic sense in the eye, in those cryptochrome molecules, runs on radical pair reactions that are insanely sensitive. We're talking about pairs of electrons whose spins are gently nudged by Earth's magnetic field. Random oscillating fields in that 20 kHz to MHz band shake those spins, scramble the chemistry, and blur the directional pattern the bird sees. To the robin, north stops being a crisp glow and turns into static. And you can actually watch the fallout in the real world. Disoriented migrants get sucked into city light domes, circling skyscrapers and stadiums on foggy nights like they're trapped in a bad screensaver. Flocks veer off traditional flyways near dense infrastructure corridors, hugging highways or power lines that were never on the original map. Collision rates with glass towers spike in big migration funnels, as if the built-in GPS is glitching right when they need it most. Now, quick pattern interrupt. If your phone's GPS lost the plot every time you walked past a Wi-Fi router or a power line, you'd throw that thing out by the end of the day. You'd be like, yeah, you heard me right. This app is useless. Speaking of, let's get back to it. We've quietly done exactly that to birds, only you can't swap out their navigation app. It's wired into their eyes. Next, we'll look at how they try to back up that fragile compass with stars, sun, and even smell, and what happens when those start glitching too. So, we've glitched their built-in compass and scrambled their sky clock. Imagine you're a bird over a featureless ocean now. No roads, no coastlines, just water in every direction and clouds hiding the stars. How on earth do you ever find a tiny island, let alone a specific burrow you dug last year? You'd think this is where even the best navigator just gives up and says, yeah, I live here now. I'm a sea creature. But some of the most extreme travelers on the planet do the opposite. Shearwaters and petrels spend most of their lives out over open water, thousands of miles from land, and then somehow bullseye the same rare speck of rock in the middle of nowhere at night and drop straight into the right nesting tunnel. No map, no GPS, no Google Earth. What if I told you they're literally smelling their way home? Not like, oh, I caught a whiff of my house and followed it. That would be way too easy. But by building a giant, invisible smell map of the ocean. Scientists call it an olfactory map, and it's basically a mental atlas made out of odors. Over the sea, different regions have different smellscapes. Tiny plankton blooms give off certain chemicals. Algae belts have another signature. Air drifting off forests or cities carries land vegetation and human pollution. Mix in things like fishy oils from feeding grounds, and you get this swirling cocktail of scents. As young birds cruise around, they learn that one blend means northwest of home, another means downwind of that big island chain, and so on. Smell isn't acting like a compass needle here. It's not pointing north. It's acting like a map. By comparing the gradients, stronger here, weaker there, this combo fading, that one getting sharper, a bird can tell, I'm south of my usual route, or I've drifted too far east. It's the difference between a single arrow and a whole street grid in your head. Now, this all sounds a bit magical, so people tried to break it. In classic human fashion, they caught shearwaters and petrels, took them far from their nesting islands, and then temporarily blocked their sense of smell with safe anesthetic sprays in the nostrils. Same birds, Same wings, same magnetic field, same stars overhead for the ones flying at night. Just no working nose. The result? The birds with intact smell shot back toward home like feathery missiles. The birds with blocked olfaction wandered, looped, or took way longer, as if someone had blurred all the labels on their mental map. They weren't helpless, but they were clearly missing a major piece of the puzzle. And that's the pattern we keep seeing. No single sense explains the whole trick. Smell gives them the map. Magnetism gives them a rough grid. The sun and stars give them direction and time. And landmarks kick in near coasts. It's all stacked, redundant, overbuilt. Which is smart, because when we start knocking out more than one of those systems at once, things get ugly. Next, we'll look at what happens when the modern world starts quietly cutting wires in that navigation network, one by one. So when that invisible wiring starts to fail, birds fall back on something you and I know really well: looking out the window. Imagine you're a pigeon, a few hundred meters up, and the world below isn't just scenery. It's a living map. Rivers, coastlines, mountain ridges, even that ugly highway interchange you complain about every morning. All of it becomes a giant set of glowing neon arrows saying, "This way home." You'd think a homing pigeon, with all its secret senses, would just be a flying GPS, drawing perfect straight lines through the sky. Nope. Believe it or not, when scientists slapped tiny GPS loggers on them, they found something way weirder. The same birds, on repeated flights, didn't take the shortest route. They took the same route, over and over. Following highways, canals, rail lines, even skirting around the same clumps of trees like they were exit ramps. It's like they're using our infrastructure as aerial roads. One study showed pigeons faithfully tracing a major motorway for kilometers, even when a direct diagonal across open fields would have saved time and energy. How's that for stubborn brand loyalty? But it tells you something huge. Once a bird locks in a visual path, that memory is sticky. The landscape isn't just background. It's a story they've memorized line by line. The wild part is how that story starts. Young birds don't wake up with a Google Maps view of their world. They build it. First, short, nervous loops around the nest. Then wider circles. Then bolder straight-line adventures to a nearby river or ridge. Each flight stitches together little patches of scenery into a bigger mental map, a cognitive atlas that says, "Okay, that red barn sits between the forest edge and the bend in the river," which points toward the distant hills. You can almost see the file slowly downloading in their brains. And this doesn't just happen in pristine wilderness. Our mess is in the file too. Skyscrapers slice up the horizon into new vertical landmarks. Wind farms spin giant white arms that birds can see from miles away. Suburbs sprawl out in repeating grids of roofs and roads. To a bird, that's all usable data. Until it isn't. Reflective glass throws fake sky and fake trees at them. Light domes over cities glow like artificial dawn, luring night migrants off course and straight into downtown death traps. What if I told you that some species are now being pulled into cities night after night, not because they like us, but because our lights and buildings have become the brightest, loudest landmarks on their map? Yeah, you heard me right. We've hacked the visual cues of millions of animals without even meaning to. So here's the scary part. Landmarks feel solid. Rivers, coasts, wetlands, snow lines on mountains. They seem like forever features. But what happens when coastlines creep inland, rivers dry into dusty scars, and wetlands vanish under farms and parking lots? When climate change redraws the very map these birds have memorized for generations, where do they go then? The scary answer is, a lot of them go to the right place at the wrong time. Imagine being hardwired to leave on a certain date because the days hit a certain length. You feel that ancient itch in your wings, and off you go. You'd think that would line up perfectly with spring, bugs, and fresh leaves like it did for your great-great-grandparents. Not anymore. This is called a phenological mismatch, which is a fancy way of saying the schedule broke. Many birds cue migration from day length and an inherited calendar, not from a weather app. But spring is shifting. In some places it comes weeks earlier, in others it stutters and arrives late. So an insect-eating songbird can fly thousands of miles, land on its breeding grounds right on time by its internal clock, and find that the caterpillar boom already happened, or hasn't happened yet. Now the adults are exhausted. The chicks hatch into a food gap, and survival nosedives. One bad year is rough. String a few of those together, across an entire flyway, and you start hollowing out populations. The navigation system still works. The destination just stopped cooperating. And it's not only timing that's moving. The map itself is sliding. As the planet warms, isotherms, those bands of equal temperature, creep poleward and uphill. Forests march north. Snow lines retreat. Wet, cool valleys dry out. Believe it or not, whole habitats are basically shifting under these animals like a slow-motion conveyor belt. So a warbler that used to breed in a cool, temperate forest now has to push farther north to find the same climate. A mountain bird has to climb higher every decade just to stay in its comfort zone until it literally runs out of mountain. Their genetic program says, "Stop here, this is home." The weather says, "Keep going." How's that for mixed signals? On top of that, we're deleting the pit stops. Long-distance migrants don't fuel up once. They hopscotch. Marsh here, estuary there, a flooded rice field or a coastal lagoon to tank up on worms and seeds. But wetlands are drained, coasts are armored and eroded, and prime mudflats turn into ports, resorts, and parking lots. Those once reliable gas stations on the Sky Highway, closed, permanently. Now connect this back to navigation. The magnetic field still points north. The stars still arc overhead. Birds follow the same invisible lines their ancestors did and touch down where the route says, "Rest stop." Except the smell of rich, salty mud is gone. The dark outline of reeds is replaced by warehouses and streetlights. The food that used to be there is just not. Zoom in with me for a second. One shorebird drops out of the sky after a non-stop ocean crossing, wings trembling, fat reserves down to fumes. It glides toward what should be a bustling, shallow marsh, the place its body has been programmed to expect. It lands in cracked mud. No water, no frogs, no insects, just dry reeds rattling in a hot wind. Then zoom back out. Multiply that one bird by thousands, then millions, all hitting their marks on a planet that keeps quietly moving the targets. The compass hasn't failed. The world under their wings has. So if the world keeps shifting under their wings, how do we actually test what's inside the bird? You'd think this is where the story gets less dramatic, more lab coat and clipboard. Nope. Imagine this. A truck full of racing pigeons, crates stacked like feathery shipping containers, rumbling down a highway hundreds of kilometers from home. The birds have never seen this landscape. No cozy rooftop loft in sight. Researchers stop at some random field, pop the crates, and a gray blur explodes into the sky. The scientists jump back in the car, hit the gas, and when they finally pull into the loft's driveway, the pigeons are already there, circling lazily as if to say, "What took you so long?" Believe it or not, that basic stunt has been repeated for decades, with scientists getting more and more evil genius about it. Release them on a clear day, and the birds lock onto the sun and familiar landmarks, drawing a straight line home like living drones. Cover the sun with thick overcast, and they still do it, just a bit messier. So what's the backup system? Researchers tried magnets. Yeah, you heard me right. Tiny magnets attached to the birds' backs, or even their heads. On sunny days, no big deal. The pigeons shrugged it off and flew home anyway. But under overcast skies, suddenly those same birds wobbled, took longer, or veered off course. It's like their invisible compass got bumped, and without the sun to cross-check, they started second-guessing themselves. Then came the smell experiments. Block a pigeon's sense of smell with little nasal plugs or anesthetic. Truck it to an unfamiliar release site. And now things really get weird. Some of those birds just wander, circling and circling, as if the map in their head has gone blank. Let them smell again, release them from the same spot, and boom, they shoot off in the right direction. What if I told you part of their map is literally an odor landscape built from wind and sea and soil? Over time, all these manipulations started to paint a picture. Pigeons aren't using one magic trick. They're running a whole stack of cues. Sun and landmarks when they can, magnetic field and smell when they have to, switching strategies depending on the conditions like a tiny autopilot choosing between GPS, road signs, and, I don't know, sniffing the air. And still, there are the failures. Famous stretches of coast where birds that usually nail the route suddenly vanish, or flocks that all get lost along the same mysterious corridor. People have blamed local magnetic anomalies, weird infrasound echoing off mountains, even strange atmospheric conditions we barely understand. It's like there are dead zones in the sky. So if a domesticated pigeon, bred by humans for races and love letters, can juggle all of this, what are wild migrants doing as they cross entire oceans at night? In the next part, we meet the birds running the full, terrifyingly advanced version of that same multi-sense algorithm. Those terrifyingly advanced birds. Some of them are still in diapers, metaphorically speaking. Imagine this. It's a clear autumn night. The adults have already left, and a tiny warbler that hatched a few weeks ago just takes off. No parents, no tour guide, no Google Maps. It launches into the dark and aims for Africa, a continent it has never seen, and somehow doesn't just end up circling the nearest gas station light. You'd think migration is all about wisdom and experience, right? Nope. A lot of first-time migrants, like warblers and shorebirds, leave at night completely alone. Young bar-tailed Godwits in Alaska head out over the Pacific and fly thousands of miles non-stop. Juvenile cuckoos in Europe point themselves toward Africa even though their parents ditched them weeks earlier. That's not family tradition. That's something burned into the brain. But here's the twist. What's pre-programmed in these baby birds isn't a full map. It's more like a simple rule set. Scientists call it clock and compass. Fly in this direction for this long. So a young bird might have an instruction like, go southwest for 6 weeks, climbing at night, resting by day. That's orientation. It knows which way to point, but not yet where it is on the planet. Older birds, though, are doing something way more intense. They show true navigation. They don't just follow a heading. They know when they're off course and correct. They can find specific rivers, the same patch of mangrove, even the same tree. What if I told you some Arctic terns can hit the same tiny feeding zones in the ocean year after year, while your phone GPS loses its mind in a parking garage? How do we know the difference? Classic evil genius science move. Displacement experiments. Researchers catch migrating birds and secretly move them hundreds or even thousands of kilometers off their normal route, then see what happens when they're released. Juveniles usually stick to the inherited program. If their genes say, go southwest, they go southwest, even if that now sends them toward the wrong continent. They miss the traditional wintering grounds entirely. Adults? Totally different story. When displaced, many of them bend their routes, turning, correcting, and still homing in on the usual winter sites. Believe it or not, some will cross open ocean or mountain ranges they've never seen from that angle and still nail it. Same species, same migration season, but two completely different levels of knowing where you are. So what does that tell us? There's a genetic baseline route, a kind of starter kit that gets refined into a real mental map by experience. Each successful migration adds detail, coastlines, wind patterns, star fields, smells, even where the good stopover wetlands are. Trip after trip, the bird's internal model of the world goes from sketchy pencil outline to full-color atlas. But guys, one of the absolute best things you can do with a system like that is keep the classroom stable. And right now, the classroom is on fire. Because this whole learning process quietly assumes the skies, the stars, and the landscapes stay roughly the same from year to year. In the next part, we'll look at what happens when that assumption breaks, and the students are left flying blind. So what happens when that classroom on fire isn't a metaphor, but an actual building? Imagine a foggy autumn night over a city skyline. One stadium blazing with floodlights, a glass skyscraper glowing like a lighthouse, low clouds turning everything into a bright white ceiling. And above that, a river of birds that should be sliding silently past suddenly gets stuck. You'd think they'd just go around it, right? Nope. Many of these migrants are nocturnal flyers, and they're not winging it at random. On clear nights, they use the stars, the faint glow of the horizon, even patterns of polarized light as a kind of built-in compass and clock. To a warbler or a thrush, the night sky is a map, a watch, and a GPS all rolled into one. Now drop a skyscraper into that system and crank the lights to maximum. In fog or low cloud, those beams scatter and bloom, creating a fake sky that's brighter than the real one. Birds lock onto it, spiral toward the glow, and start circling. They call, more birds hear them and join, and suddenly you've got thousands of tiny, exhausted creatures trapped in a cone of light they can't quite escape. Believe it or not, we've watched this play out in brutal detail. At some TV and radio towers, single nights have killed thousands of birds, their bodies piling up around the base. Offshore oil platforms in the North Sea and Gulf of Mexico have reported snowstorms of migrants smashing into the rig when the deck lights are left blazing in fog. In big cities, one all-glass office block can end a migration for hundreds of warblers and thrushes before sunrise. And it's not just the impact. Many birds circle until they literally drop from exhaustion or veer off into unfamiliar territory and never recover. What if I told you that the same light that helps you find your car in a parking garage can erase a journey that started 3,000 miles away? Yeah, you heard me right. Remember that quantum compass in the robin's eye? Cryptochrome needs very specific light conditions to let birds see Earth's magnetic field, slam their night sky with intense, broad-spectrum light, and you're not only hiding the stars, you might be scrambling the chemistry that underpins their magnetic sense. Some experiments near cities show birds losing their magnetic bearings in noisy, lit-up environments, then regaining them when the lights and radio noise are reduced. Here's the wild part, and it's a bit of a pattern interrupt in this horror story. The fix, at least for this piece, is almost embarrassingly simple. Turn the lights off, or at least way down, during peak migration nights. Timers, motion sensors, closing the blinds, darkening just a few upper floors. Tiny human habits that can save thousands of animals. We'll come back to specific actions you and your city can take. But first, we need to look at the other invisible forces that can knock a bird's compass off balance. So we've dimmed the lights, but imagine you're still a bird trying to thread your way through our world. Navigation isn't just north, south, left, right. It's a three-dimensional obstacle course, now packed with spinning blades, hanging wires, and giant glass walls you literally can't see until you hit them. You'd think the sky would be the last wild place we couldn't mess up, right? Nope. A lot of the ancient migratory corridors birds use just happen to run along windy mountain ridges, narrow valleys, and coastal passes. Great for birds catching a free ride on updrafts. Also great for humans putting wind farms exactly in those same spots. So a route that worked perfectly for thousands of years suddenly turns into a gauntlet of turbines they can't really avoid without burning way more energy. Picture an Arctic tern or a bar-tailed Godwit locked into a flyway that stretches thousands of miles. It's following magnetic lines, the curve of a coastline, maybe even the smell of the sea. It doesn't know there's now a forest of 300-foot towers waiting on the ridge ahead. It just knows. This is the path my species takes. This is the line in the sky my body is programmed to follow. And it's not just the big, obvious stuff. Some of the deadliest hazards are practically invisible. Power lines don't register as solid objects until a bird is already on top of them, especially in fog, at dusk, or when it's focused on a landmark. One wrong angle, one gust of wind, and that perfect internal compass delivers you straight into a cable you never evolved to recognize. Glass might be even worse. Reflective windows can look like open sky or a continuation of trees behind you. So a bird's landmark system does its job, lines up with what looks like a safe gap, and full-speed impact. With a pain that, to its brain, didn't exist. Believe it or not, some cities lose hundreds of thousands of animals a year this way, one silent thud at a time. The wild part is how small design tweaks can flip this from deadly to manageable. Paint just one turbine blade black and collision risk drops. Add simple markers or spirals to power lines, and suddenly they pop against the background. Use bird-safe glass with tiny patterns or UV stripes, and the window becomes visible to birds but still looks clear to you. How's that for an easy win that doesn't mean shutting down the grid or turning off the wind? What if I told you the real key is understanding how birds actually see space and direction in the first place? If we can map their magnetic sense, their star maps, their favorite landmarks, we can start redesigning our structures to speak their language instead of silently killing them. And once you see the world the way a migrating bird does, some of our everyday technology starts to look a lot more dangerous than you'd expect. And once you see the world the way a migrating bird does, our cities stop looking harmless and start looking like giant, glowing traps. Because here's the part we almost never think about. These birds are not sightseeing. They are running on an energy budget so tight that one wrong turn can literally kill them. Imagine you're a bar-tailed Godwit, this rare little long-distance athlete that looks like a normal shorebird but secretly flies like a jet. One female Godwit was tracked flying over 11,000 kilometers non-stop across the Pacific. No breaks, no snacks, no floating on the waves, just wings. Before she leaves, she doubles her weight in fat, then burns through almost every gram. By the time she lands, she's basically a feathered skeleton with a heartbeat. You'd think a bird that hardcore has plenty of wiggle room, right? Nope. The math is brutal. That fat isn't a cushion, it's a countdown timer. Every extra hour in the air is more fuel gone, more muscle burned, more chance that there's nothing left when she finally sees land. Add even a 5 or 10% detour to an 11,000-kilometer trip, and suddenly you're flying hundreds of extra kilometers on fumes. Now throw in real-world chaos. A crosswind shoves you sideways for a few hours. A bank of city lights lures you inland when you should stay over the dark ocean. Radio noise scrambles your magnetic sense just enough that your perfect line turns into a slow curve. You don't notice in the moment. But by the time you do, the tank is empty. Believe it or not, that tiny error can be the difference between making it to a rich coastal wetland and stalling out over a parking lot. That's when you get the emergency landings. People wake up and find warblers stunned on their balconies, seabirds circling oil rigs like lost planes, exhausted migrants dropping onto cargo ships or random fields that look nothing like the habitat their bodies were built for. They didn't choose that spot. Their navigation plan was so finely tuned that once it's disrupted, they just crash wherever gravity wins. And this isn't some one-off tragedy for a single creature. Scale it up. When millions of birds migrate, and each one has slightly higher odds of being blown off course, starving mid-flight, or landing in a dead-end landscape, you don't just lose a few unlucky individuals. Over a couple of decades, whole populations start to slide. Numbers fall, breeding success drops, and suddenly that common bird your grandparents remember is on a red list. What if I told you some species are already right on that edge, and we only just got the tracking tech to watch their roots falling apart in real time? Yeah, you heard me right. The maps we're drawing now are shocking. And in the next part, we're going to follow one of those failing journeys step by step. So we've got these migration routes crumbling under pressure, but now, for the first time in history, we can actually watch the cracks form in real time. And it all starts with something that looks like a chunky price tag. Lightweight GPS and satellite tags used to be huge, strapped only to big birds like eagles and storks. You'd think that was enough. Nope. Engineers kept shrinking them until some are now lighter than a paperclip, small enough to ride on tiny songbirds and shorebirds without slowing them down. Imagine a backpack the size of your thumbnail, quietly recording every twist and turn as a creature crosses an entire ocean. When scientists started downloading those tracks, the first reaction was basically, wait. They do what? Arctic terns, famous for going from the Arctic to Antarctica and back, don't just fly in a straight heroic line. They zigzag hard, dropping into S-shaped curves to surf wind currents, shaving days off the trip and saving precious energy. Bar-tailed Godwits, on the other hand, launch into 7,000-plus-mile non-stop flights across the Pacific, tracing almost perfect great circle routes, the shortest path on a sphere, like they've got a geometry app built into their skulls. And then there's the spooky precision. The same individual sandpiper, tagged year after year, will leave its Arctic breeding ground, cross continents, and land on the exact same muddy pond behind some random village fish farm. Not roughly that wetland. The same patch of shoreline, sometimes within a few hundred meters. How's that for a built-in GPS that never needs an update? Once you stack thousands of these tracks, the sky roads start to glow. We see birds making huge detours around storm systems you and I only notice on a weather app. We see them suddenly climb thousands of feet to clear a mountain range, then drop back down on the other side like nothing happened. They tweak departure times by hours or days to catch tailwinds, or pause mid-journey when headwinds turn a safe hop into a death march. Believe it or not, every simple migration is full of tiny navigation decisions, and the surprises keep coming. Some populations we thought were one big happy family actually split into totally different flyways, one group hugging coasts, another cutting straight over open water. As climate shifts, a few bold individuals start probing new stopovers, testing warmer routes, and if they survive, others copy them. You can literally see shortcuts appear over a bird's lifetime as it edits its inherited map. Now flip the camera for a second. Imagine a Godwit could see our GPS traces, traffic jams, coffee detours, panicked U-turns because you missed the exit again. Compared to its clean, ancient sky highways, our routes would look like a toddler scribbled on the planet. Speaking of, let's get back to it, because in the next part, we're going to zoom in on one of those scribbles, a single failing journey, and watch where the guidance system starts to break. And guys, before we follow that failing journey off a cliff, this is actually a good moment to land for a second. We've been migrating through a lot of big ideas, so think of this as a quick rest stop on our own flyway. Because imagine you're not just watching birds on a screen. You're out there with them. It's 5 a.m. The sky is that weird blue-gray that makes everything look like a ghost, and you're standing in a muddy field with binoculars, a thermos, and one very questionable life choice: deciding to leave your warm bed. I've done dawn bird counts like that. You'd think it's all peaceful nature documentary vibes. Nope. It's cold, your fingers stop working, your phone battery dies at 20% for no reason, and the one time a rare creature finally flies over, you're busy wrestling with a broken zipper. How's that for tragic timing? That's where today's sponsor, Trailline, actually fits this story. Trailline makes gear that's built for people who are out there chasing animals, storms, or just their own curiosity and don't want their stuff to quit before they do. Believe it or not, the jacket I'm wearing in half of my field shots in this series is theirs. On that miserable 5 a.m. Godwit survey I told you about, it was raining sideways. The only things that survived were the birds and my Trailline shell. It's fully waterproof, but still breathes, so you're not doing that portable sauna thing every time you walk up a hill. Long hike, long stakeout, long travel day on a bus with no aircon. It's just comfortable. Their field pack has battery for days. I ran GPS tracking, notes, and camera batteries off a single power brick and still had juice to check maps on the way home. Great for your gear, great for your sanity, really just keeps you from becoming that person begging strangers for a charger at a gas station. And because your brain is the first thing to tap out when you're tired and cold, they bundle in access to their Focus app with guided breaks and checklists. Sounds cheesy, but when you're trying to spot a tiny bird against a giant sky, not forgetting the basics actually matters. If you want to check them out, Trailline is giving viewers 20% off your first order, plus a free travel mug. Just use the code BIRDFLIGHT at checkout or hit the link in the description. When you do, you're not just getting better gear, you're directly helping fund deep dive documentaries like this one, instead of, I don't know, another unboxing video of a plastic shark toy. Because a good jacket, a solid battery, a focused brain, that's your version of a homing pigeon's compass. Reliable, boring, always there when you need it. Speaking of, let's get back to it, because next we're going to push bird navigation to the edge with experiments that sound almost cruel, but revealed abilities so precise it honestly freaked scientists out. So scientists basically said, okay, cool compass, but what happens if we kidnap the bird? Yeah, you heard me right. Imagine you're a tiny migrating creature, minding your own business, and suddenly a human scoops you up, puts you in a box, and flies you thousands of kilometers in the wrong direction just to see what you do next. These are real experiments. Researchers have grabbed birds mid-migration, loaded them onto planes or ships, and secretly dropped them off on totally unfamiliar coasts. No landmarks they know, wrong side of an ocean, sometimes even a different continent. Then they open the box, step back, and watch. Do the birds panic? Do they just pick a random way and hope for the best? You'd think so. But what actually happens is way stranger. Start with the rookies. Juvenile birds, on their first big trip, tend to follow a simple built-in rule. Fly this direction for this long. It's like having only one arrow on your map. So when scientists displaced young starlings and some geese hundreds or thousands of kilometers, those kids just kept going in their inherited direction and ended up in completely the wrong place. Wrong country, wrong coastline, same stubborn little brain saying, "The program says go southwest, so I'm going southwest." Now compare that with the adults. Same species, same kidnapping, totally different outcome. Experienced birds, when released, don't just continue on autopilot. They bend their paths, curve around entire seas, and still manage to reach their traditional wintering grounds. Believe it or not, some storks moved across Europe and even into Asia, rerouted across whole basins, and still nailed their usual spots, as if someone quietly handed them an updated map mid-flight. This is where we hit the idea of true navigation. Not just knowing which way is north or south, but knowing where you are relative to a goal, even from a place you've never seen before. It's the difference between a basic compass and opening a map in a city you've never visited and instantly going, "Oh, I'm here. I need to be there." What if I told you birds can do that after being blind relocated over oceans in the dark? Seabirds take it to another level. Shearwaters that get shipped across entire ocean basins somehow arc back along smart routes, as if they carry a rough mental sketch of coastlines and wind patterns. Some of them seem to tie this map to Earth's magnetic field and even smell, using giant odor landscapes over the sea to lock onto home. How's that for a built-in GPS with no battery? And remember, this is all running in a brain the size of a grape. So if a kidnapped bird can wake up in a foreign sky, check invisible magnetic lines, sniff the air, and solve a problem we'd need satellites for, what hidden computations are happening in there that we still don't understand? And more importantly, what happens when we start scrambling those signals? So let's zoom in. If the magnetic field and the stars are the outside tools, what on earth is handling all that inside a brain the size of a grapeseed? There's a tiny region in a bird's brain that keeps popping up in navigation studies. It's called the hippocampus. And you'd think a word like that belongs in a medical textbook, not inside a sparrow. But this little chunk of tissue is basically the bird's internal map room, the place where spatial memories, routes, and landmarks get filed away so they can fly straight instead of doing confused circles over the ocean. Here's where it gets wild. In species that really lean on memory to survive, the hippocampus is supersized. Food-caching birds that hide thousands of seeds in different spots? They've got a beefed-up hippocampus compared to close relatives that don't cache. Long-distance migrants that cross continents? Same story. Imagine a chickadee with a tiny built-in storage unit labeled, "All the places I buried snacks last fall," and you're not that far off. Inside that region, individual neurons act like little GPS pins. Some fire only when the bird is in a particular place, others when it's facing a particular direction. Scientists call the mammal versions place cells and head direction cells, and birds seem to have their own analogs humming away. Believe it or not, you can watch a neuron light up over and over as a pigeon passes the same rooftop corner, like the brain is saying, "Yep, here again." Different cells respond to different spots and headings, and together they sketch out a mental grid of the world. And it's not a static grid. In homing pigeons and migratory species, those navigation hubs actually change shape with the seasons. Before migration, areas linked to orientation and memory swell with new cells and stronger connections, as if the brain is downloading the latest map update. After the journey, some of that extra tissue shrinks back. How's that for a limited time upgrade? Your phone struggles with a software update. This animal literally remodels its brain for a trip. What if I told you none of this requires a giant human-style atlas in their head? Birds seem to compress an insane amount of spatial and directional information into minimal hardware. Instead of one perfect master map, they stack simple rules. Follow this coastline. Keep that star pattern at this angle. Adjust when the smell of the sea hits a certain strength. Layer enough of those tiny rules, and suddenly a bar-tailed Godwit can cross the Pacific in one non-stop flight without checking Google Maps once. And yet, even with all these elegant circuits, some behaviors just don't add up. Whole flocks suddenly abandon traditional routes. Long-standing stopover sites go quiet. Sometimes, entire populations seem to vanish from known flyways, as if they slipped through a crack in our understanding. So if we've mapped the brain's obvious navigation tools already, what hidden switches are still buried in there, waiting to explain the next impossible turn? So here's the twist. Long before we had GPS tags or brain scans, people were already reading those impossible turns in the sky like a calendar and a map. Imagine standing on the deck of a wooden ship, no satellite in sight, and your best navigation tool is a flock of birds. Sailors did this constantly. You'd think the middle of the ocean is just endless water, right? Nope. When they started seeing terns, gulls, or flocks of shearwaters heading in a steady line at dusk, that was the hint. Land is that way. These rare, repeatable sightings were like living road signs. Farmers did the same thing on land. The first swallows under the eaves, cranes circling high and calling at dawn, geese stitching V-shapes across the sky. Those weren't just nice birds. They were the start gun for planting, harvesting, and moving herds. And then there are the myths. In a lot of cultures, migrating birds weren't just animals, they were messengers. Some stories say cranes carry souls between worlds. Others describe flocks as spirits following a sky road or sky river that only they can see. Believe it or not, that language is weirdly close to how scientists now talk about flyways, invisible highways, branching routes, predictable exits and on-ramps. But talk to elders almost anywhere and you'll hear a quieter, more unsettling chapter. Local stories of lost migrations. Grandparents who remember autumn skies going dark with birds, while their grandkids see a handful at best. Fishers who used to time their trips by the first storm petrels and now say, yeah, they're late. Or they just don't come. In other places, people talk about new birds showing up. Tropical species on northern farms, desert birds at city ponds, decades before climate papers finally said, oh, the routes are shifting. What if I told you those casual comments are now data? Today, you've got birders and regular neighbors logging first arrival dates on apps, reporting mass movements on radar, flagging a single rare creature that shows up wildly off course. One person's, that's odd, becomes a dot on a map. Thousands of dots turn into a new flyway, or proof that an old one is breaking apart. Scientists overlay those reports with satellite tags, weather maps, even magnetic field models. Suddenly, the folklore line, "The swallows are late this year," turns into a graph showing spring creeping earlier, stopover wetlands drying, and whole populations nudged north. Here's the pattern interrupt. An old carving shows birds following a glowing river across the night sky, a cosmic path between worlds. Next to it, on a modern laptop, a satellite track of Arctic terns arcs across the globe in a tight, bright ribbon, almost the same shape. One is myth, one is hard data, and together they're whispering the same thing. There really are roads in the sky. So now the question is, what happens when we start tearing pieces of those roads up? So we're ripping up the roads in the sky. But what if I told you those roads aren't just painted in stars and magnetism? What if the birds are also reading things we barely even notice, and sometimes not at all? Imagine this. Days before a hurricane makes landfall, before the radar maps turn blood red, satellite tags show entire flocks quietly veering off their usual routes. No panicked news alerts, no dramatic music, just a clean, sharp turn away from where the storm will be. You'd think that was a coincidence, right? Except it keeps showing up in the data. And it's not just storms. There are those eerie reports from earthquakes, too. Chickens refusing to go into coops. Pigeons exploding off rooftops. Wild birds going dead silent minutes or hours before the ground moves. Ancient stories. Modern security cameras. The same weird pattern. Are they just jumpy little animals, or is there another layer of the planet they're tuned into that we're basically deaf to? One big suspect is something you actually carry in your phone's weather app. Pressure. Birds have internal barometers built right into their bodies. Tiny sensors in their ears and bones let them feel changes in atmospheric pressure the way you feel that pop in your ears on a plane, but way more precise. When a low-pressure system, the kind that breeds storms, starts to deepen, some migrants delay departure, others leave early, and some climb to different altitudes to hitch a ride on better tailwinds and dodge brutal headwinds. Believe it or not, that alone can be life or death. If you're a bar-tailed Godwit trying to cross 7,000 miles of ocean non-stop, flying straight into a jet of bad air isn't just annoying, it's a crash and burn decision. So they tweak timing, height, even the exact line they fly, all off invisible pressure waves we only notice when the weather app icon changes. But pressure might just be the warm-up act. There's another idea that sounds like science fiction: infrasound. These are sounds so low you can't hear them at all, but they can travel thousands of miles. Massive ocean waves slamming into coastlines, distant storms, even tectonic plates grinding can send out these deep rumbles. Some scientists think birds might pick those up, like a global subwoofer humming away under everything. If that's true, a bird over the Atlantic could, in theory, hear a storm brewing days away, or sense the low growl of shifting rock before an earthquake. Yeah, you heard me right. While we're arguing about whether 5G or radio towers are messing with their magnet compasses, they might be quietly listening to an entire hidden soundtrack of the planet we barely know exists. Now, to be clear, the evidence here is messy. It's not like the rock-solid stuff we have for magnetic fields or star maps. Some studies see patterns, others don't, and birds are annoyingly bad at filling out surveys. But that's exactly the point. Every time we think we've listed all the senses an animal can have, something rare and inconvenient pops up and proves us wrong. So if storms and quakes are just background noise to them, what else are they hearing, feeling, or seeing that we're missing? Because the next clue to how they cross the planet might not be in the sky at all. It might be in the way the whole Earth itself vibrates under their wings. But when you're riding the planet like that, on senses we barely understand, the margin for error is tiny. And sometimes, it goes spectacularly wrong. Imagine you're birdwatching on a quiet New England beach, and you spot a tiny olive green warbler. Cute. Except this one is supposed to be in Europe, not just a little off, thousands of kilometers off. Every year, these vagrants show up. European warblers in North America, Asian shorebirds poking around European mudflats, even tropical birds standing in the snow like, yeah, you heard me right. This is fine. You'd think these are just random lost souls, but there's a pattern hiding in the chaos. A lot of these birds didn't pick the wrong distance. They picked the mirror image of the right direction. Juveniles especially will launch on their first migration with nothing but an inherited rule set in their heads. Fly X degrees for Y days. Flip one of those genetic compass settings, and instead of southwest to Africa, they go southeast to the middle of nowhere or end up on the opposite side of the ocean. Right script. Wrong sign. What if I told you this isn't just a one-off glitch, but a whole category of mistake called mirror image migration? Same stamina, same timing, same internal clock, but the compass needle is reversed. On a neat map of migration routes, it looks almost satisfying. All these tidy lines arcing one way, and then a few rebels arcing the exact opposite, like the bird equivalent of taking the wrong exit and not realizing until the road signs are in another language. And that's just the solo disasters. Sometimes the sky itself turns on them. Picture this: a huge wave of migrants crossing the Gulf of Mexico at night, riding favorable winds. Then a storm front slams in, or a city's lights bloom into a glowing trap. By morning, beaches are carpeted with exhausted birds, or downtown streets are littered with stunned warblers and thrushes that slammed into glass after circling lights until their fuel tanks ran dry. One bad night, tens of thousands grounded. These failures aren't random bad luck. They're stress tests on the system. A tiny mutation in a gene that sets their preferred compass angle, a magnetic anomaly from buried rock, or a wall of radio noise and LED glare that scrambles their magnetic sense for just a few hours. Any of that can cascade into a route error big enough to move a creature an entire continent off course. The program is precise, but it's also fragile. Now zoom out with me. You see a global map covered in elegant migration lines, all flowing like veins across the planet. Then, pattern interrupt. One lonely dot, way off in the wrong ocean. Cut in tight. It's not a dot anymore. It's a single bird, sitting on a foreign shore, surrounded by the wrong plants, the wrong smells, the wrong stars. And somehow, it still has to decide. Keep going, turn back, or rewrite the map entirely. Because hidden in those mistakes is our next clue: how birds learn, adjust, and sometimes turn an error into a brand new route. Imagine that lost bird we just left on the wrong shore is not just one confused traveler, but the key to an entire species' future. For some birds, navigation isn't just about getting home on time. It's the thin line between survival and disappearing forever. Some species don't have flexible, "Hey, we'll figure it out" routes. They run on razor-thin margins, locked into extremely specific flyways and pit stops. A single estuary where they refuel. One chain of wetlands where they rest. You'd think a bird that can cross oceans would have options, right? Believe it or not, lose one of those key sites, and the whole migration can unravel. Take long-distance shorebirds that race to the Arctic. Their entire breeding year is timed to one short explosion of insects. If they arrive even a few days late, the bug buffet is already over. Chicks hatch into a silent tundra with empty skies, and suddenly the world's most epic commute turns into a one-way trip to a population crash. How's that for a missed connection? Or picture cranes that have used the same staging lake for centuries, maybe thousands of years. Generations of birds landing on the same mudflats in the same valley, guided by ancestors that knew every bend in the river. Drain that wetland for farms, build a city over it, light it up all night, and those cranes don't just lose a resting spot. They lose a chapter of their migration story that their bodies still expect to find. Where do you go when your map leads to a parking lot? Now here's the really scary part. Small populations can't afford to experiment. When there are millions of birds, a few bold individuals can try a new shortcut, follow a different coastline, test a different stopover. Most will fail, but a handful might survive and quietly write a new route into tradition. When you're down to a few hundred? If your pioneers don't make it, that experiment doesn't just die. The species does. This is where inherited versus learned navigation comes crashing together. The genetic program might still say, fly northwest for 6 days, then turn south at the coastline. But the coastline has moved under rising seas. The marsh is now a shrimp farm. And if the elders who remember the backup plan are shot, or collide with city lights, or vanish in a storm of radio noise, that cultural GPS blinks out. You're left with a crude, outdated script running in a world that's been completely redrawn. What if I told you that some of the most spectacular migrations on Earth are already running on this kind of borrowed time? That whole sky rivers of birds you and I still take for granted might be something your kids only see in old footage? Because the next question is brutal. Can birds rewrite their maps fast enough? Or are we watching the last draft in real time? So if we really are watching the last draft in real time, we need to meet the birds that are writing the wildest chapters. Imagine an animal that doesn't just fly south for winter. It literally chases summer around the planet like it has a frequent flyer card. That's the Arctic Tern. Tiny, white and gray, looks pretty unassuming. But this creature breeds in the Arctic, then launches all the way to Antarctica, then back again, every single year. We're talking up to 70,000 kilometers annually. Yeah, you heard me right. That's like flying from New York to Sydney and back, 3 times, and then tacking on a bonus road trip. You'd think they'd take the shortest line on the map. Nope. Tracking tags showed they weave and curve, dropping down along rich ocean fronts, swinging around storms, and timing their trip so they stay in the light as much as possible. They're literally surfing the edge of daylight, living an almost endless summer to feed and fly, while we complain about a 6-hour layover. Now crank the difficulty up again. Meet the Bar-tailed Godwit. This bird does an 11,000-kilometer Pacific crossing in one go. No pit stops. No floating break on some random log. Just days and days of continuous flapping over a flat blue nothing where, if you mess up your navigation, there is no second chance. You don't get a little lost out there. You just don't arrive. So how do they pull that off? They stack every navigation tool birds have. A built-in magnetic sense gives them the broad direction, like a planet-sized compass, always humming in the background. The sun by day, the stars and even polarized light patterns by night act as a moving map and clock. High-altitude wind patterns become invisible highways they can climb into or drop out of. And when they finally creep near land, some seabirds even switch on an odor map, smelling their way along coasts and plankton-rich water, as if the ocean has street signs made of scent. For a long time, we thought this was all just hardwired instinct. Hit start, follow program, hope for the best. But recent satellite tags on terns and godwits blew that up. Individuals have been caught mid-journey, suddenly bending their routes hundreds of kilometers to grab a tailwind, or climbing to crazy altitudes to hop on a faster current. That's real-time decision-making layered on top of an inherited script, like your phone's GPS rerouting around traffic, except your phone doesn't have to flap the whole way. And it raises a brutal question. As we heat the planet, scramble wind patterns, shift food zones, and clutter coasts with light and steel, how many of these ultra-marathons are still going to be runnable? Can even the best navigators on Earth keep threading that needle when we're busy moving the eye of it? So if those marathon flyers are threading a moving needle, I want to show you the bird that doesn't even get to watch someone else sew. Imagine being born into the wrong family. On purpose. Cuckoos are professional imposters. The females sneak into other birds' nests, drop off an egg that's a pretty good color match, and bail. No parenting, no bedtime stories, no, this is the way to Africa, kid. The foster parents, usually much smaller songbirds, just raise this odd, fast-growing chick as if nothing is weird, as if this giant baby bird bulldozing their real kids is totally fine. You'd think that would completely wreck any chance of learning how to migrate, right? No one is showing these chicks a route, a map, not even a vibe. But here's where it gets wild. When the foster family's own young take off on their usual local migration, the cuckoo chick stays behind. It hangs around for weeks, eating, molting, practicing short flights. Then, one day, it just goes. No parents, no flock, no older birds to follow. This is a solo flight. And yet, that young cuckoo heads out of Europe and somehow finds its way to the exact same African wintering grounds as the biological parents it has never met and will never see. Yeah, you heard me right. First-time flyer, thousands of kilometers, bullseye. What if I told you this isn't a one-off miracle, but the rule? Tracking studies with tiny satellite tags have followed these birds, and the routes are not some simple fly southwest and hope for the best line. Young cuckoos make multi-leg journeys with specific stopovers, like refueling in southern Europe, then crossing the Sahara, then shifting routes again once they hit Central Africa. They even adjust paths when they're blown off course, as if there's a built-in rerouting system quietly recalculating. So what does that tell us? It screams genetic programming. The timing of departure, the general direction, the sequence of habitat types to aim for, maybe even how long to stay at each stopover. All of that is apparently encoded in DNA. This isn't cultural knowledge passed down by a flock. It's like a preloaded app you can't uninstall, running on a brain that's a few grams at most. And remember, these are not rare lab birds raised in some navigation boot camp. These are wild animals that were literally raised by the wrong species. No one gave them a flying lesson. Yet the software still boots up and runs. How's that for both impressive and terrifying? Because if the code is that hardwired, here's the scary edge. What happens when the climate scrambles wind patterns, dries out those stopover wetlands, or shifts insect hatches by a month? When the inherited route says, land here, refuel here, and here doesn't exist anymore. Do they rewrite the code on the fly, or are we about to watch one of nature's most precise programs start crashing in real time? And just when you're thinking, okay, navigation is a hardwired program? Cool. The story takes a quantum left turn, straight into the eyes of a robin. Imagine a tiny European robin in a lab. It's spring. Hormones are screaming, time to migrate. And this little creature is bouncing against one side of a funnel-shaped cage, all its restlessness aimed in the exact direction it wants to fly. No map, no older birds. Just access to the night sky, a normal magnetic field, and boom. Its body leans towards Scandinavia like it's reading an invisible road sign. You'd think if you bring a bird indoors, you kind of break the spell, right? Nope. Researchers built special rooms where they could control everything: the light, the star patterns, and, most importantly, the magnetic field. Then they started messing with that field like a kid spinning a globe. Rotate Earth's magnetic field in the room by, say, 120 degrees. The robins calmly re-aim their restless hopping by. 120 degrees. Weaken the field? Their orientation gets fuzzy, like a bad GPS signal. Add a second, oscillating magnetic field on top? In some settings, the compass doesn't just drift, it collapses. Here's where it gets really weird. In one set of experiments, scientists didn't crank the fields up. They added a whisper. Low-level radio frequency noise, in very specific bands, the kind of background buzz you'd barely notice from electronics and power lines. Suddenly, the robin's magnetic sense went haywire. Birds that had been pointing neatly in their migration direction started acting like they had no clue which way was north, south, or anything in between. Believe it or not, when the researchers shielded the room with metal to block that radio noise, the compass snapped back. Same birds, same season, same setup. Only difference was the electromagnetic static in the air. How's that for fragile? You don't get that kind of sensitivity from a simple iron filing stuck in the beak. You get it from something quantum level, where tiny changes in energy nudge chemical reactions one way or another. Which brings us to the robin's eye. Inside the retina, there's a light-sensitive protein called cryptochrome. When blue light hits it, it forms paired electrons that can be nudged by magnetic fields, like a microscopic coin flip that either glows one way or another. Genetic work showed that when specific cryptochrome variants are missing or altered, the magnetic sense just fails. Same bird, same brain, same wings, no working cryptochrome, no compass. Pattern interrupt for you. What if I told you that every time you walked past a Wi-Fi router, your internal sense of direction shut off? You'd step into a cafe, forget which way home is, walk out, and suddenly remember. Yeah, you heard me right. For robins and other birds, that's not a sci-fi horror pitch. It's uncomfortably close to what we're building into their world. And what if I told you we're not just adding a little background noise to that world? We're basically rewriting the sky in a single human lifetime. Imagine the gap between your grandparents being born and you watching this video. In that tiny slice of time, we've changed the cues birds use more than they changed in the millions of years before. That's not an exaggeration. That's lights, noise, concrete, and climate, all slammed into the same few decades. Start with the stars. For a night-migrating bird, the sky used to be a clean map, bright band of the Milky Way, clear constellations, predictable patterns. Now, in a lot of cities, the only constellation is the row of LED billboards over the highway. Artificial light doesn't just drown out the stars, it lures birds off course, pulls them into downtown glass canyons, and keeps them circling until they slam into buildings or drop from exhaustion. Then we stack on the invisible stuff. Remember that robin losing its quantum compass next to a Wi-Fi router? Scale that up. Radio towers, cell networks, radar, 5G, power lines humming all night. You'd think a creature that can cross an ocean without stopping would be hard to confuse, right? Believe it or not, a bit of electromagnetic noise at just the wrong frequency can scramble that delicate magnetic sense and turn a precise migration into a drunk walk. And while we're busy doing that, we're also moving the goalposts. Winds are shifting as the climate heats up. Storms are getting nastier. and the safe refueling spots birds used to rely on are drying out, flooding, or turning into suburbs. A bar-tailed Godwit that evolved to ride steady tailwinds across the Pacific now hits headwinds, heat, and empty mudflats where rich feeding grounds used to be. On top of that, we're building literal walls across their highways in the sky. City skylines, wind farms placed right on flyways, endless glass, even offshore platforms. From a bird's eye view, that progress looks like a maze of new hazards jammed into routes that once were wide open. Here's the scary part. These navigation systems were tuned over millions of years. Tiny genetic tweaks, tested over countless migrations, slowly locked in what works. We've asked them to update the software in, what, 50 years? Genes can't comfortably keep up with a construction schedule. Can birds adjust at all? Yeah, you heard me right. They're not helpless. Some species are already shifting routes north, leaving earlier, learning new landmarks like highways and windbreaks, even changing which stopover sites they use. Young birds can imprint on different coasts and mountain ranges, and a few migrations are actually cultural, passed down like family road trip directions. But that only works if enough birds survive the chaos to teach the next generation. If the teachers vanish, the map goes with them. So the question hanging over all of this is simple and brutal. Are we going to give them that chance? Or will some of the most astonishing migrations on Earth end not with a bang, but with a quiet, empty sky each spring where there should have been wings? Imagine you hit pause on the chaos for a second and zoom in, not on the whole flock, but on one single bird. Same species, same route, same basic map in its head as its neighbors, but it leaves a week earlier, or it flies a little higher, or it's just a tiny bit better at sensing the magnetic field. That's microevolution in action. You'd think all robins or godwits are running the exact same program, but they're not. Inside a population, there's a spread of timing, routes, and even how sensitive their built-in GPS is. When the world changes, the birds whose settings happen to fit the new reality survive a bit more, raise a few extra chicks, and, generation by generation, those traits stop being rare and start being normal. Believe it or not, we're already watching that happen in real time. In Europe and North America, some migratory birds are shifting their schedules, arriving on breeding grounds earlier as springs warm up. Others are shortening their journeys entirely, choosing to overwinter in cities where heat islands, bird feeders, and streetlights create these weird artificial oases. A few species are even adding new stopovers on their flyways, dropping into sewage ponds and urban wetlands that didn't exist a century ago. How's that for improvising with the mess we've made? But there's a catch. Not every creature can pivot that fast. Long-lived birds that don't breed until they're several years old, or that only raise a couple of chicks at a time, simply don't shuffle their genes quickly enough to keep up with a climate that's lurching from one record to the next. If you're a specialist that needs a very specific wetland, or a narrow mountain pass, or one tiny island to rest on, you can't just say, "Cool, I'll use a parking lot instead." One bad year can wipe out decades of slow, careful evolution. Now tie that back to navigation. A young cuckoo can still launch for Africa with nothing but genetic instructions, its internal compass set to a certain angle relative to the magnetic field and a rough distance. Those angles can drift over generations as the birds that hit the right spots survive. But what if the magnetic backdrop itself is being scrambled by radio noise? What if the winds and temperatures that used to match that compass heading have shifted hundreds of kilometers north? At some point, the map can update only so fast, while the world under it is moving like a conveyor belt on fast forward. The risk isn't just getting a little lost, its whole lineages flying faithfully into empty oceans, dry marshes, and cities that pull them off course with light and glass. And here's the twist. Whether adaptation wins this race may depend less on what's inside the birds and more on what we choose to do with our lights, our buildings, and our carbon in the next few decades. So what happens if we don't hit the brakes, and the sky itself starts sending us warning signs? If the sky starts sending warning signs, we've got two options: ignore them, or learn the language and redesign our whole world so birds can actually read it again. Once you understand how a bird sees direction, magnetic fields in the eye, stars as a spinning map, coastlines as glowing highways of smell and memory, you realize something wild. Every building, every light, every spinning turbine is either helping that map stay clear or scribbling graffiti all over it. You'd think concrete and glass are neutral, right? Believe it or not, for a migrating warbler, a glass tower can look like an endless forest reflected in the sky. So we start with the obvious villain: windows. A lot of bird-safe glass isn't magic force fields, it's just patterns. Dots, stripes, UV markings that break up those mirror-like reflections and tell a flying creature, "Solid wall ahead, don't even try it." It's the same pane of glass to you, but to a bird, the visual code flips from tunnel to barrier in an instant. How's that for low-tech saving lives? Then there's light. Night migrants aim using stars and the faint band of the Milky Way, and we've basically painted over that with a giant orange highlighter pen called Sky Glow. Shielded lights that point down, warmer colors, and motion sensors don't just save energy. They stop cities from becoming glowing traps. Imagine if every skyscraper dimmed or switched off. Non-essential lights during peak migration weeks, when billions of birds are pouring overhead. That's not a cute gesture. That's the difference between a clean corridor and a lethal maze. Timing is huge. Birds don't move randomly. They pulse through in waves, on specific nights, in specific seasons. So airports can schedule spotlight-heavy maintenance outside those windows. Offshore rigs can go into dark mode for a few critical weeks. Even your own house can join in. Guys, one of the absolute best things you can do is kill the porch lights on strong migration nights. Tiny change, massive ripple. And then we get to the really big toys: wind farms and other tall structures. What if I told you we can see bird highways from space now? Tracking tags and radar show narrow migration bottlenecks, the avian equivalent of rush hour bridges. Put your turbines just a bit to the side of those lanes, and suddenly you're making clean energy without setting up a spinning obstacle course. This is where policy sneaks in. Imagine zoning laws that don't just ask, "Is this good for traffic?" but also, "Is this in the middle of a flyway?" Environmental impact assessments that have to include migration maps, not just a token bird survey. And because a sandpiper doesn't care where your border is, you get international flyway treaties, cities along the same route agreeing on lights-out nights like a coordinated air traffic control for animals. Pattern interrupt for your brain. Picture a city map where the main roads aren't for cars at all. They're invisible bird highways arcing overhead, bright blue lines showing where flocks move, and everything we build has to respect them. Some streets capped low, some rooftops dark and quiet, some stretches of sky deliberately left open, like protected lanes in the air. That's the future we're quietly designing every time we flip a switch, approve a tower, or draw a zoning line. The only question is, do we keep pretending the sky is empty space? Or do we start planning for the travelers we almost never see? So let's zoom way in. That giant, glowing web of flight paths and satellite maps we've been talking about. It runs straight through your living room window. Imagine a warbler that's just flown 1,000 miles over open water. It's running on fat reserves, instinct, and vibes at this point. To that bird, your window, your yard, your little porch light are not random human clutter. They're coordinates on a map it's been following since before it hatched. You'd think one window couldn't matter in a journey that big, right? Believe it or not, those one windows add up. In North America alone, up to 1 billion birds die each year from window collisions. Not 1 billion over history. 1 billion per year. That's the kind of number that quietly erases species while we're brushing our teeth. So what can you actually do from your couch? Guys, one of the absolute best things you can do is deal with light. Migrating birds use the stars like a built-in GPS. Our cities turn those stars into a glowing, confusing soup. If you can, turn off outdoor lights at night during peak migration in spring and fall. If you need them for safety, shield them so they point down, not up into the sky like a budget lighthouse. Next target, the glass. Birds don't understand reflections. They see sky and trees and go full send. Simple fixes work. Decals spaced closely across the pane, faint patterns, or exterior screens break up that deadly mirror. It doesn't have to look like you sticker-bombed your house unless you're into that, in which case, go wild. And then there are the tiny backyard predators. Your cat might seem like a sleepy little couch creature, but outside during migration, it's basically a stealth drone with whiskers. Keeping cats indoors or supervised in a catio during peak movement turns your yard from a hunting ground into an actual rest stop. Speaking of rest stops, birds don't just need safe air. They need somewhere to crash, eat, and refuel. Planting native trees and shrubs gives them real food, insects, berries, seeds. A shallow water dish or small pond becomes a gas station and shower combo. Skip the pesticides that nuke the insects, because you're not just killing bugs, you're stripping the menu off every stopover on that flyway. And if you want to level up from passive helper to active data point, join the swarm of people feeding information back to scientists. Log your first spring hummingbird or the day that flock of geese shows up. Report any window strikes. Jump into local bird counts. Those dots on a map help refine migration models way more than one lab ever could. What if I told you your home might literally be the difference between a bird making it to its breeding grounds or not? Once you start noticing migration, hearing the night flight calls, seeing silhouettes slip across the moon, you will never look at your own windows or the night sky the same way again. Once you start noticing, you can't stop. But here's the problem. Most of what birds use to navigate is invisible to you and me. So how do we even begin to see their world? Imagine you could turn on a special filter over the planet and suddenly Earth's magnetic field pops into view. Field lines swooping from pole to pole, colors showing where it's strong, where it's weak, how steeply it dives into the ground. You'd think that sounds like a sci-fi movie overlay, right? Nope. That's literally what some apps and animations do now. You drag your finger across a globe, and you see inclination angles and intensity changing like weather. It's our best guess at the magnetic grid a robin or a godwit might be reading with its eyes. And once you've seen that grid, global flyway maps hit completely differently. These aren't just random squiggles of birds going north and south. They're like glowing highways wrapping the planet. Thick bands of arrows show where millions of birds move together. Thinner threads peel off toward rare, isolated routes, the avian equivalent of a back road only a few weirdos take. When you stack different species on top of each other, you suddenly see choke points, narrow coastlines, river mouths, tiny wetlands. One drained marsh in the wrong spot, and you've basically put a roadblock on an international bird freeway. Believe it or not, planetariums have become some of the best migration classrooms on Earth. They'll kill the lights, spin up the night sky for a specific date, and then overlay the paths of night-flying songbirds across the dome. You lie back, and above you, constellations stay fixed, while these faint streams of birds pour past, riding star patterns and the arc of the Milky Way. Some shows even simulate polarized light, those hidden sky stripes birds see that we totally miss. It's like being inside a bird's head, minus the feathers and the constant urge to scream at 5 a.m. Out in the real world, augmented reality takes it a step further. Hold up your phone, and an app can paint the magnetic field direction on the horizon, highlight major flyways overhead, or ghost in the sun's path for the day, so you see the compass cues a young cuckoo might be using on its first solo trip to Africa. What if I told you that, with the right filter, your boring commute route is actually under a transcontinental superhighway for wings? These tools aren't just cool visual party tricks. City planners use flyway maps to argue against putting skyscrapers and brutal light pollution right in the middle of migration corridors. Wind farm designers can see where turbines would slice straight through a raptor highway and shift them a few kilometers. Conservation teams pull up those layered maps to show a government, look, this one muddy estuary is a gas station for half a hemisphere of shorebirds. When you can see the risk, it's a lot harder to pretend it isn't there. And here's where it gets a little uncomfortable. Once you've seen the invisible scaffolding birds are using, the magnetic lines, the star grids, the crowded aerial highways, you can't unsee it. Every lit tower, every drained wetland, every new offshore project looks different. In the final stretch, we're going to pull all of this together and ask a bigger question. If we finally understand the map birds are following, what does that force us to do next? So now that we've pulled the camera back and seen the whole sky full of invisible highways, let's zoom in for a second on what's actually inside a bird that makes any of this possible. Because you'd think, with all our satellites and apps, we'd have this cracked by now, right? Nope. Imagine a little warbler as a kind of flying stack of navigation systems. At the base, there's a genetic program, a built-in urge that says, fly southwest for this many weeks, then stop. Young cuckoos do that without ever meeting their parents, which is wild. On top of that, you've got the sun by day, the stars by night, and even polarized light patterns at dawn and dusk acting like a backup compass and clock when clouds roll in. Then there's the magnetic field. In some birds, special molecules called cryptochromes in the eye react to Earth's magnetic field and literally change how the world looks, like a faint overlay only they can see. Other experiments hint at iron-based sensors buried somewhere in the head or beak. Smell adds another layer. Seabirds can follow giant odor maps over the ocean, tracking plankton and wind like a scent-based GPS. And once a route is learned, visual landmarks, coastlines, rivers, city edges, lock everything in, turning a vague path into a razor-sharp corridor. So on paper, it sounds neat and tidy. Genes, sky, magnetism, smell, landmarks. Stack them and boom, perfect navigation. But believe it or not, some of the most basic questions are still just question marks. Where exactly are those magnetoreceptors? Are they in the eye, the inner ear, scattered through nerves like tiny compasses? How does a brain the size of a walnut decide what to trust when the sun says one thing, the smell says another, and a thunderstorm is scrambling the magnetic field? And we're not even sure that's the full toolkit. Some scientists think birds might be listening to infrasound, those super low rumbles from oceans and mountains, or even picking up tiny electric fields in the air. Sounds a bit sci-fi, but then you remember we already know they're running quantum chemistry in their eyeballs. Yeah, you heard me right. In European robins and probably a bunch of other species, pairs of electrons in cryptochrome molecules get briefly entangled with Earth's magnetic field. Quantum entangled. The same kind of physics we use in fancy labs and Nobel Prize speeches, a backyard bird is using to decide whether to turn left over the Baltic Sea. How's that for humbling? And here's the part we really can't fake. You can strap a GPS tag on a bar-tailed Godwit and watch it fly 11,000 kilometers non-stop across the Pacific. You can build models, run simulations, write equations, but you will never know what it feels like, from the inside, to lift off into darkness and feel north, or home, as a physical sensation in your bones. On a whiteboard, this story is a list of mechanisms: genes, sun, stars, quantum compasses, odor maps. It's tidy, almost boring. But step outside one autumn night, look up, and picture a single bird leaving a quiet marsh, wings beating into the black. No signs, no roads, no phone. Just an invisible path etched into its body and the sky, and it follows. In the next part, we're going to ask a harder question. Now that we know that path is real, what happens when we start cutting through it? So when that invisible path starts to fray, it's not just a bird problem, it's a reality problem. Imagine the sky as a giant glowing map only some creatures can see, and every autumn and spring it lights up with arrows of geese, warblers, godwits, terns. When those arrows start blinking out, that's the visible sign that the invisible order underneath is breaking. You'd think, okay, sad, fewer birds, less pretty sunsets, and move on. But those migrations are like veins in a living body. Birds aren't just commuting for fun. They're hauling nutrients, seeds, and energy from one end of the planet to the other. A shorebird that feeds in the Arctic and winters in New Zealand is literally moving the Arctic south in tiny packets of nitrogen and phosphorus every time it lands and, does its business. Take insect-eating swallows and warblers. When their routes fail or their timing slips, insects explode in number, crops suffer, forests change, disease risk goes up. Nectar-feeding birds miss blooming seasons, and suddenly some plants don't get pollinated across whole mountain ranges. Believe it or not, a lost flock can mean hungry people, stressed farms, and forests that quietly start to die back decades later. And this is all riding on senses we barely experience. If a robin can see magnetism, what else is out there that we're walking through blind every single day? Other animals read electric fields in water, feel polarized light patterns in the sky, pick up faint seismic cues before earthquakes. Our human window on reality is like watching a 4K movie on a cracked old phone while everyone else in the theater has IMAX. What if I told you that while we're patting ourselves on the back for GPS and satellite networks, a baby cuckoo is flying thousands of kilometers to Africa using a built-in map it never had to download? Our tech is powerful, sure, but it's clumsy. Your phone freaks out in a tunnel. A bar-tailed Godwit crosses 7,000 miles of ocean non-stop and nails the same muddy patch of estuary. How's that for version 1.0 navigation? And yet we're flooding that ancient system with noise. Radio towers, city glow, radar, 5G, glass skyscrapers. Yeah, you heard me right. We're literally wallpapering the planet in signals and lights, and then acting surprised when birds slam into buildings or spiral off course. We don't just risk losing a rare animal here or there. We risk erasing a whole layer of planetary organization we only started to understand yesterday. So this isn't about charity for cute creatures with wings. It's about deciding what kind of world you and I want to live in. One where the sky is just empty air over highways and strip malls, or one where, twice a year, the air still fills with living arrows, stories written across the clouds in feathers and flight. In the final part, we're going to pull all of this together and talk about what you can actually do to keep those stories from fading out. So let's pull this whole thing into one breath. Imagine you're that shorebird we started with, a bar-tailed Godwit lifting off from Alaska and aiming for a tiny patch of mud on the far side of the Pacific. You're not checking Google Maps. You're running a navigation system baked into your bones and tuned by a lifetime in the sky. First layer, you're born with a rough plan. A direction, a season, a kind of built-in schedule that says, when the days feel like this and the air smells like that, you go southwest for this long. Young cuckoos do exactly that, flying thousands of kilometers to Africa with zero help from mom and dad. You'd think that would end in a lot of very lost baby birds. Somehow, it doesn't. Second layer, family and culture. Geese, cranes, storks. They don't just flap around at random. They learn the actual route, the safe valleys and refueling wetlands, by following older birds who've done this trip for years. It's like getting handed a living road atlas, updated every generation. On top of that, you've got the sky tools, a sun compass by day, a star map by night, and even patterns of polarized light that leak through clouds, turning the whole dome above you into a giant clock and compass. Arctic terns use that to run their world tours from pole to pole and back again, racking up 70,000 kilometers a year like it's a casual commute. How's that for frequent flyer miles? Then there's the secret sense. European robins literally see Earth's magnetic field using quantum reactions in special molecules in their eyes. Yeah, you heard me right. Quantum bird vision. That magnetic grid gives them a rough, "you are here" overlay, even in the dark, even in fog. Now add smell and memory. Seabirds can sniff out invisible islands by following giant odor maps drawn by plankton, wind, and waves. Coastal birds memorize shorelines, rivers, mountain silhouettes, even city skylines, stitching together a mental picture so detailed they can hit the same patch of beach within a few hundred meters, year after year. Stack all of that, and our little Godwit crossing the Pacific doesn't look like magic anymore. It looks like the one-time genetics, family lessons, stars, sun, magnetism, smell, and memory all agree on the same answer at the same moment. One slip, one broken piece, and that landing never happens. And that's the catch. Light and noise scramble those compasses. Climate change shifts the wind maps and food stops. Glass and towers turn ancient flyways into obstacle courses. Believe it or not, your city's glow can matter to a bird that's never even landed there. So when you watch a V of geese overhead, or a single robin in your yard, you're looking at the end point of this insane, layered guidance system running on instinct and experience. The question now is simple. Do we keep the sky readable, or do we jam the signal? In the next part, we're going to talk about what you can actually do to stay on the right side of that choice. So let's stay on that right side for a second, because this is where you actually come into the story. Imagine every porch light, every glass tower, every tiny backyard window as a little edit on that invisible map birds are reading. You don't control the whole sky, but you do control your few pixels of it. Guys, one of the absolute best things you can do is ridiculously simple. Flip a switch. During peak migration nights in spring and fall, turn off unnecessary outdoor lights, close the blinds, or at least aim lights down instead of into the sky. You'd think one balcony or one office floor doesn't matter, right? Believe it or not, when thousands of just one people do that in a city, collision deaths drop by tens of thousands of birds a season. Next level, make the glass less deadly. Those huge, clean windows we love? Birds read the reflection as more sky. A few stripes of tape, dot decals, or patterned film on big panes breaks that illusion. It looks like a design choice to you, but to a warbler doing 30 miles an hour, it's the difference between a clean pass and a full-speed impact. How's that for a home makeover with an actual body count attached? And it's not just you versus the skyscrapers. You can push your city, your school, your workplace to adopt bird-friendly building rules. Ask about lights-out policies for tall buildings, support local rules that require bird-safe glass on new construction, back candidates who talk about light pollution like it's a real thing, because it is. What if I told you a city council vote can protect more migrants in one night than you'll see in your whole life? On the ground, those sky roads need pit stops, wetlands, little woodlots, scruffy parks along rivers. Those are the gas stations and motels on a 7,000-mile trip. Support the people guarding them. That might mean a donation to a wetlands trust, joining a local bird club that restores habitat, or backing global flyway projects trying to keep key stopovers from turning into parking lots. It's not glamorous, but neither is flying over the Pacific for 8 days straight. You can also help by feeding the map with data. Join citizen science projects that log migration nights, share local migration forecasts, or report window strikes so researchers actually know where the worst black spots are. Next time you see a flock chattering across the stars or hear that messy dawn chorus outside your window, can you imagine the invisible lines they're following? And one small thing you could do this week to keep those lines intact? If this changed how you see the night sky, like the video, share it so more people stop jamming the signal, and subscribe for more deep dive nature stories. Then pick one concrete thing, one light, one window, one email about a local policy, and make your corner of the sky a little safer for the travelers passing overhead. So if a secret compass was hiding in backyard robins this whole time, what else are we missing? Imagine this. We spent decades watching birds, banding them, tracking them on maps, and we still didn't realize some of them can literally see Earth's magnetic field in their eyes. You'd think a glowing force field overlay on reality would be kind of hard to miss, right? Nope. It was sitting in plain sight, blinking at us from the hedge. And that's the part that really gets me. If we overlooked an entire sense in animals we share parks and parking lots with, what's hiding in the deep ocean, or in the rainforest canopy, or under your feet in the soil right now? What if I told you our 5 senses are basically the budget version of what's actually possible on this planet? Take sharks. Some species can detect electric fields so faint they can feel the heartbeat of a fish buried in sand, as if the whole ocean has Wi-Fi and they're the only ones with the password. Snakes? A bunch of them see infrared, turning warm bodies into glowing targets in the dark. Bees read polarized light patterns in the sky, using a sun compass even when the sun is behind clouds. Same world, totally different worlds. How's that for a plot twist? Once you start pulling on that thread, it gets wild fast. Could there be animals that sense the slow bending of rock before an earthquake, like a built-in tectonic early warning system? Are there deep-sea creatures that feel the shape of ocean currents the way we feel wind on our face, navigating invisible rivers we don't even have names for? Maybe some tiny insect is tracking chemical signatures in the air so complex that, to us, it would be like reading a novel made of smells. We already know some seabirds can smell their way home across thousands of miles of open water, following giant odor maps written by plankton and wind. So who says that's the limit? Believe it or not, we might be surrounded by animals quietly plugged into channels of information our brains simply can't tune to. So I want to throw this to you guys. Which animal sense blows your mind the most? If you could borrow one creature's perception for a day, shark electrosense, snake infrared, bird magnetic vision, bee polarized skylines, anything, what would you pick, and what would you actually go do with it? Tell me in the comments, because I'm really curious what world you'd choose to step into. And as we keep decoding how birds navigate, here's the catch. We should probably assume we're still missing something. Maybe several somethings. Every new discovery is a reminder to be careful about how much noise we add to the planet's signals, because we don't always know who's listening, or how. In the next part, we're going to look at what that means for the future of migration, and for us. So imagine this. We're back where we started. It's barely dawn. The sky is that deep blue that almost feels like the inside of an eyelid, and on the horizon, there's this thin line of orange that hasn't decided to be sunrise yet. Then you hear it before you really see it. A low, rolling rush of wings and calls. And suddenly, the whole sky fills with birds. Tens of thousands of tiny silhouettes, sliding across the first light like moving constellations. They're following invisible highways that were already old when the first cities were just campfires, when nobody had drawn a border, when written language was still just a weird idea. You'd think it's chaos up there. It's not. Every turn, every climb, every pause at some muddy wetland is part of a route that's been tuned and retuned over millions of years. Now, what if I told you to freeze that frame, and then erase it? Same coastline, same horizon, same season. But this time, the sky is empty. No calls, no shadows, just the hum of traffic and a couple of planes dragging contrails across the silence like signatures on a blank page. The route is still there in their genes, in the Earth's magnetic field, in the stars. The birds just can't follow it anymore. Not because they forgot, because we made the map unreadable. A glass tower here, a strip mall there, a wetland paved into a parking lot with really great lighting, as if the one thing the night sky needed was more LEDs. 1,000 small cuts, lights left on, windows unmarked, habitats sliced into pieces, noise poured into the frequencies they use to listen to the planet. Birds know where to fly because the Earth itself has been whispering directions to them for millions of years. We've started shouting over that whisper. With every new satellite, every brighter billboard, every lost patch of shoreline, we're turning up the volume on our side and drowning out theirs. But it doesn't have to end with an empty sky. Believe it or not, we already know how to turn the volume down. Technologically, we can shield lights, map safer flight paths, design glass that birds can actually see. Politically, we can protect stopover sites and migration corridors the way we protect national parks. Personally, guys, one of the absolute best things you can do is ridiculously simple. Flip a switch. Lights off. Curtains closed. Stickers on windows. Support the people fighting to keep these routes alive. Because we're living in the tiny, rare moment in history when these migrations still exist and we still understand just enough to save them. The question is, do you want to be part of the generation that kept the sky full? Or the one that watched the last great flocks vanish without even realizing what was lost? And if this is what's at stake for birds, imagine what else is listening to the planet's signals right now, quietly depending on them, while we decide how loud we want to be.